University of Espírito Santo, and I'm going to present PolKA, Polynomial Key-Based Architecture for High-Performance One, hopefully. And I would like, first of all, to thank you for the opportunity to present our work in this group, High-Performance One Research Group. And then also important to mention that all the credits are to our amazing team here, Christina, Rafael, Moisés, all these people that are here. All the credits are to them, because they are working really hard to make this proposal to evolve. So this is a work between two institutions, UFES and IFES. Just very briefly, this is a state in Espírito Santo, Brazil, where we are located here. So this is a map of the state, where UFES, my university, has 5 campi, and IFES has 22. And both of the institutes are located in this capital, Vitória, where actually we have this Software-Defined Networks Research Group. This is the NERDS group. And the mission of this group is to innovate in network system, especially in the areas of software-defined networks, NFV, autonomous networks. And this is a photo of the small data centers in our university of the NERDS. And I hope you can check it after if you are interested. So the agenda for today, really, I'm going to present a motivation proposal, the design we've been thinking, some prototype applications really briefly, and conclusions and future works. So just to align with the HPWAN mission, which is to enable ultra-fast, resilient, and adaptive data paths, more focus here, our focus is more on data science, and more recently AI-driven workloads. We really trust, really believe that SDN and network programmability, they can help a lot in terms of innovation of protocols. PolKA is exactly what we are investing for some time. However, when you consider the bottlenecks, the packet forward based on table lookup has some bottlenecks. It requires, for example, large number of states, so network scalability can be a problem. The granularity is limited by the capacity of switch tables, and also there is can have a low latency for path configuration, which can affect agility for path configuration. An alternative to tackle these problems, yes, we think source route is an interesting approach, because source specifies a path and adds a route label to the packet header, a very classic way. And the most traditional way is list-based source route, or source controlled routing, where a path is represented as a list of ports or a stack of labels, which is the case of MPLS in this example, where the edge pushes a stack, 100 and these labels that are here, and sends to the first node S1. And each node, it's a very simple example where each node just matches on top label and performs a pop and sends it to the next hop S2. And this operation is repeated all these S1, S3 until it reaches to the edge and the packet is delivered to the application. So just to illustrate really briefly, what are the limitations in this approach? One is related to the forwarding state, which is in the packet, which means that we need to rewrite operation like push, pop, and swap. A second limitation could be related to the variable size of headers, which can affect the number of encoded hops, and they are not fully stateless, because they still rely on per node forwarding tables in the core. This is the case of MPLS, FEV lookup, segment routing, and beer forwarding tables. So what is our proposal? Is PolKA proposal is the idea is to design exactly a source routing approach to meet all these requirements. So it should be topology agnostic, fixed header size with encoded path, no tables in the core, so that it should be deployable, of course, in programmable suites. So the main idea of PolKA is to use the polynomial residual number system, RNS, and using the Chinese remainder theorem in order to calculate some parts of the protocol. And we propose to make the packet forward based on a very elementary arithmetic operation, which is remainder of division. Which means that in this case, the path is encoded in a root label, and each node only decodes with its own key. So next, I'm going to present the design. How does PolKA work? This is based in 3 polynomials, one for a route ID, which identifies a route identifier calculated exactly using CRT. The node ID is a very specific polynomial. You can think about it as a prime number, so it's a reducible polynomial, and a port ID identifies the ports of each core node. And the forwarding uses exactly the mod operation, which is the route ID that is in the packet divided by the node ID will give the port ID. Now, a very simple example to illustrate the concept. The hosts are connected to the edges, in this case, and the edges are connected to a fabric of core nodes. Then the controller assigns a reducible polynomial to the core nodes, as we can see in the figure, and the ports are represented by the numbers around. We can see the identifiers of the ports in each node. Well, we can select then a path for a specific flow. For example, this set of red switches with output ports in blue in this figure. Then this is the representation, polynomial representation, and then which is important is how can you get the route ID, which is the result of a congruent system, Galois field 2. We are representing exactly this x in green, x here, and this is the result of the solution for this route that we presented before. So in terms of forwarding operation along the path, it means that if you put exactly this number at the switch, the result will give by the module, by this route ID, by the node ID, will give the output port as we mentioned before. So now, very briefly, how it works in more detail. So the flow entry is added in the route ID is added by the edge node, which sends to the next hop. Then the forwarding is going to be by the mod operation, as you mentioned before, by this route ID and the specific node ID. We give this output 1. Important to mention that there is no route ID rewrite. It means that the route ID remains unchangeable along the whole path, and then sends to the next hop that does the same operation until it reaches to the edge, which is going to remove the route ID and deliver to the destination in a transparent way. So just to give the general concept of the approach. So now a very big challenge is, okay, how can we implement this module operation efficiently in data plane? Because P4 language, for example, does not have natively support for mod operation. But we found out a way to reuse the CRC in order to calculate the model in a very efficient way. So this is one example where we assign this polynomial, irreducible polynomial to the generator polynomial, and then we do 2 shifts, so shift right, shift left, XOR, and we leave the CRC in execution, and then an XOR, then you obtain exactly the output port from the CRC that's already there. You don't need to deploy a new circuit to do a very efficient module operation. So is PolKA scalable? So if you look at the table table-based SDN, and if you want to move from blue flow from this blue route to the red line, we need to update all these switches along the path. This is not the case with PolKA, because all the communication states are stored at the edge for encapsulation. So there is no need to update all the points, just an update at the edge in order to move from the route blue to the route red. Is PolKA scalable in terms of number of nodes? So this is the way to, if you want to calculate the length of the route ID in terms of the route, we need to look at the degree of the polynomials. So this is just an analytical view. So in this study we select the node ID with the lowest possible degree for a given topology. And then we analyze the longest path, which is the diameter, for data center M1 topologies in the paper. We can see more details, but just one of the results. Then we take like a size of network with this size, number of ports, and this diameter. We need, for example, for Gen 49 bits. But what is most important, if you decide to implement using the CRC, the scalability of the road ID is directly linked to the CRC size. So 8, 16, and 32. So this is the result in practical way. It's a product of the number of hops times the CRC degree. Now, the problem is, of course, we need to have enough irreducible polynomial to represent all the nodes in the topology. So if you use 8, there are 30 irreducible polynomials, but in the case of 16, there are thousands, for 4,000, and for 32, millions. So it means that it's really scalable in terms of CRC. Now, a really practical way to position, very simple way, not giving all the details, but if you use a PolKA for CRC, then we can have this size of 10 hops with 20 bytes, with CRC 33, 40 bytes, which is quite comparison, or if for CRC 16, it's better, much better than the existing standards. So some prototype very briefly. Because of this technique, PolKA received in 2001 a Google Research Scholar Award, and then it encouraged us to deploy this approach in a testbed, in a RAR testbed, in a GN network. I'm going to detail a little bit more. After that, one developer the main developer, Xaba, incorporated in a free router topology the protocol as the first known standard protocol in the platform. Then we keep doing because we submit for Intel connectivity research, and then we got some Tofino suites which allow us to build this global P4 lab where we could deploy in a new testbed and developing the protocol itself. So now really some quickly results. This is deployment of the first one, where we try to compare to make a comparison with list-based and table-based approach in this test bed. So 4 nodes: Amsterdam, Poznan, Budapest, and Frankfurt, with 2 paths, blue and red. So in terms of performance, the throughput in this longest path was the same as the listed-based source routing or table-based layer 2. In terms of when we increase the packet size, the throughput is 10 giga basically. And also in terms of for latency, which means that the performance of PolKA matches the traditional approach. After that, as I mentioned, we have been trying to extend the global P4 testbed, not only in Europe, but also in Brazil, these suites, and also integrate with more US free router deployments. In 2023, we achieved 100 giga line speed in a Caltech testbed, where we aggregate multiple TCP flows, as we can see here, reaching the 100 giga in a demonstration over 2 PolKA tunnels. So this is the setup in 2023. Then 2024, we got a little bit more in terms of setup, but more than that, there is let's say a long distance experimentation from Vitória to Atlanta to the Caltech booth, where we cross RNP and MLite in order to reach the booth. And then we made a lot of experiments in the challenge of transmitting the tsunami challenge that happens in the supercomputer 25, where we aggregated, they achieved 12 terabits per second, and we are here exactly. But just to mention that PolKA was not the bottleneck here, just these variations because of the competition along the commercial and production networks. But it's important to say that we reached exactly the right rate in long distance communication. So now, really, almost the last slides, just to mention like a very recently, the Very Ruby Observatory. This is a collaborative use case that we are working together. So the telescope delivers, for example, in this use case, 13 gigabytes images every 27 seconds from Chile to US data facility in order to process. The challenge is the longest distance RTT with no loss, basically. And it's important to mention, I think people from MLite, they are present in the session. They have been adopted by MLite, and we are integrating PolKA in the MLite pipeline. So now, just one slide in terms of plan for supercomputer 2025. Our plan is to achieve 400 gigabits. So this is the subtype we have there. So we are going to make all this aggregation of 100 giga in order to reach the 400. Also to increase the size in terms of intercontinental tests for Vera Rubin use case. And more recently, we are implementing eBPF in order to take these nodes to the endpoints and have more control at the end not only in the network pods. Some conclusions in future work. First, takeaway message for a PolKA approach is that PolKA delivers a high-performance network solution. We're using the CRC hardware, support line rate performance of packet forward and programmable switches. It has been validated at multiple test bags, starting with 10 giga, then 100 giga. Recently, we are trying to 400 giga, and many demonstrations in supercomputing 22, 23, 24, now in 25, as I mentioned. Second takeaway message in terms of scalability. It's scalable because network state is defined only at the edge, so we face the network scalability like that. PolKA has a stateless core with tableless nodes, which enables the selection of any path. Then we tackle final granularity, which allows to assign flows and make traffic engineer optimization for the applications, and low latency on path configuration because we only need to update a single table entry at the edge. So we also provide some agility. Future work, we really believe that there is a potential to help on the HPWAN mission to support network challenges. For example, for high throughput over longer distance with stable paths and fast path configuration to recover from transient failures. Recently, I mentioned there is a collaboration, a use case for multi-site AI training workloads with Jordi from Qualcomm. He was the one to suggest and helped us in this opportunity in HPWAN. So this is the distributed AI they need synchronized and high bandwidth connectivity, and our current work is to design a framework, mathematical framework based on the quantitative theory of bottlenecks, QBS, and integrate with PolKA routing approach. And because of PolKA provides on-demand routing configuration, we can use any path, not only a subset of minimal paths, and also decide some policy-based selection, which can help on improving training time for machine learning training times. So this is just a selection of our recent publications, just for people that are interested. Some general reference. I'd like to thank you for your attention. I'm happy to take your questions. Thank you very much.